Okay, guys, this is chapter 3 is about the nuclear chemistry. You can read the PowerPoints, you can read the chapter from the eBook. However, I will be concentrating myself on certain topics, correct? That will be type of radiation we have, balancing nuclear equation, correct? That's the second one, and type of nuclear reaction. And then the fourth topic is half-life calculations. So those are the four most important topics in the whole chapter, and it's not a really difficult chapter. It's a very nice chapter, and you can read the history behind the whole radioactivity. I'm not going through, but Madame Curie, she has a unit, honored herself with the unit. She worked in this area with her husband. Unfortunately, they did not take all the precautions. Her husband had lost, I think, one eye, one arm, whatever, so disfigured. So working with the radioactivity or radioactive material or elements has a lot of side effects and a lot of disadvantages. So as I said, she was pioneering in this, and she was honored with the unit called Curie. That's the biological activity of radiation. So anyway, this is from Poland. I think it's Polish woman, Mary Curie. So she worked in that with other scientists as well, but mostly with her husband. But anyway, so this is just historic stuff. You can go and read about this. I'm not spending time on this. I'm spending time on what type of radiation. So we are dealing, as I say, we are dealing with elements that all the elements can give you radiation naturally, correct? But we are looking at the ones, the large element, large atoms. They tend to have a lot of collision within the nuclei themselves and producing a lot of radiation. So we'll go first of all, we'll look at types of radiation we are looking at. As I said, I'll leave it to you to read the history. I'll leave it to you the whole development, the whole radioactive stuff here. But the main thing of radioactivity is producing those radiation, and there are too many reasons, but one major reason is the element is just too large, and therefore the collision within the nuclei, protons and neutrons inside the nucleus is large enough to get this radiation out. And remember that this chapter 3 has to do with what? The nucleus. Chapter 2 has to do with the valence electron outside the nucleus. But when we speak about nuclear chemistry, it has not to do with the valence electrons. It has not to do with electrons outside, electron density outside the atom. Are you following me here? Now, chapter 3, we are just concentrating ourselves in the core and the center of the atom called nucleus. And with this nuclei of the elements, we will see there's a lot of radioactivity procedures or radiation coming out. So let's look at this. What types of radiations we are looking at? What type of radiation? Let me see here. Type of radiation, there are about 6 radiation, I think. So first of all, that's what we are interested in, types of radiation. As I said, can read the history, can read radioactivity and everything, but those we are dealing with, the radiation, which most probably is occurring naturally. It's just too large, the atoms are too large, and you have too many protons and neutrons inside the nucleus. They're circulating with each other, and then this collision will release some of those radiation out. So, type of radiation. We have alpha radiation. This is alpha radiation. This is called alpha here. Alpha radiation. Alpha radiation. So alpha radiation, it turns out to be is helium atom with atomic mass or mass number 4 and atomic number 2. Okay, so atomic mass or mass number and atomic number and mass number. So you have 4 and 2. This is alpha, and the alpha radiation is positively, turns out to be positively, it's a positive radiation in general. So it turns out to be positive radiation. Remember Rutherford used it. This is number 1. Number 2, I have beta. It's called beta radiation. Beta radiation is electrons with atomic mass is 0, has no mass, 0, atomic number -1 or atomic charge, atomic number or charge. This is atomic number or charge. The beta radiation is atomic mass is 0, has no mass, and -1. Now you will say this is electron. Well, this electron is not coming from valence electron outside. Those electrons are coming from the nucleus, from the nucleus. So here it is. When the protons and neutrons are colliding with each other, they are producing a lot of other stuff, and some of the other stuff are negatively charged particles, correct? So this called particle, correct? And this is called particles. Both of them are coming from the nucleus, nothing from valence electrons outside. That's all coming from this collision among neutrons and protons within the nuclei themselves, okay? So number 3, if I have a negative charge coming out, then I will have positive charge as well. So this 4 here, called number 3 here, is number 3, positron, BOS, positron. Positron is the opposite of a beta radiation. Which is the mass still 0, no mass, but the charge is, or atomic number is +1. Atomic number or charge is +1, correct? That's called positron. Now, some textbook, they don't like this. They take the E out, say this is like electron. They put a P, so it does not really matter. So they put, okay, they put B. Well, I like to be E, but it's not electrons. Electrons are always negative, but they put B. But sometimes the B is kept for the protons themselves. But anyway, so this is, again, those are particles, still particle. Number 4, we have neutrons by themselves too. So we have neutrons, radiation coming out as radiation, correct? This is particle as well. Neutron is N, just write it here. N, that's symbol of neutron. The mass of it, it has a mass, is 1, but does not have a charge, correct? The charge of it is 0, correct? Neutron, they do have masses, but no charge. They do have mass, but no charge. So, that's still particle too. Number 5, we have protons. Maybe, can I take one out and add one? Take one out, and then I'll put them in a very nice matter. So I'll put them. Can I take one out? Everybody has them? Okay, take one out and then look at the protons. Proton has the mass, atomic mass number 1, atomic number or charge plus 1, 1. Both of them 1, 1. It's wrote this H. That's the reason we give the positron P, correct? Not the E. The E is for electrons. Again, those electrons and positrons and the protons here, neutrons, all those coming from the nuclei. Nothing is coming from outside valence electrons. Everything. This is number what? 1, 2, 3. How many that? This is number 5, correct? The last thing, this is particle, by the way. Number 6. Number 6 is gamma radiation. Now, this is an issue here with this. Gamma radiation is not particles. Not particles. They are waves. Okay? Gamma are waves, not particles. Meaning, if I have a concrete wall here behind me, and if I put gamma, gamma can go through the wall. Correct? The alpha and beta might go a little bit to small, tiny depth inside the wall, but they cannot penetrate all the way. So that's the difference. Particles can go and bounce back, or can go a little bit in depth, but they cannot go further, go through an object. Are you following me here? So alpha, beta cannot go through objects. And the other protons, the same thing, neutrons, the same thing. So all those positrons, the same thing. They cannot go. The only can go through object is gamma radiation. And it has the symbol gamma, atomic mass, 0, correct? And atomic number or charge is 0. Everything 0, they can go through, correct? Can go through. That's what we call antimatter, correct? So gamma is like antimatter stuff. It's like a ghost going through the wall. So yeah, so it's nothing changed. You have an atom in excited state will be more stabilized if just moving from gamma excited state to gamma normal gamma radiation, which is no atomic mass and no atomic charge. In the other radiation, you will see some of them they have atomic charge, some of them they have atomic mass, either or. But both of them they have 0, 0. That has to be not a particle. So not a particle. So that's number 6. We have 6 of those, correct? So let's look again. Uh, the only not particle is gamma. So let's look again and look at them in some organized way. Can I take one out? Okay, let's put them in a very nice organized way so we can follow them here. So we have number one, alpha, correct? Radiation. And we have alpha 4, 2, or sometimes written just helium. It's an atom, helium atom, with 4 atomic mass and 2 atomic number. Then you have beta, radiation. You have beta 0 mass, -1, or E -1. Correct? You have positron radiation. Positron is P, and it has 0 but +1. Mass is 0, and sometimes people will write it +1. So whatever you like is positron P, or you just put it. The main thing is the charge has to be positive. The charge has to be positive. Number 4, we have neutron radiation. N, correct? It has 1 of mass, 0 charge or 0 atomic number. Charge or atomic number meaning the same thing in nuclear chemistry. Number 5, you have protons, radiation here, and this is H1 and 1. I did not see one like this, P1 and 1, but if you find it, that's it means protons, but I want that's different from the positron here. So this is different from whatever you have. Positrons have no masses, no mass. Protons does have, okay. And this is 1, by the way. So this is 1 here, guys. This is 1. Okay, number 6. Gamma radiation, and it has only 1. Gamma 0, and the atomic mass 0, and the atomic number or charge is 0. So all those 5s, all those 5 here are particles, and this is non-particles. Okay, guys. So so that's just the whole thing. Now, this is the first type of the radiation we have to really pay attention of. Now we have to do those radiation, which we give them in the sense of nuclear reaction. So when we kill radiation, then we have, let me see here. We call this one here, all this radiation, we call all this one here, okay? We call them a decay. This is nuclear what? Reaction. Nuclear what? Reaction. So those 6, those can cause what? Can cause decay, means something will be chopped out of the nucleus and new elements will come out. So let's look at what we can see of this decay or type of nuclear reactions here. Can I take this one out? Everybody has it? Okay, so everybody has this. So let's look at, now I will have uranium, the atomic mass of uranium, how much? 235. What's uranium is U? 235 or 238? 238. It has two isotopes, 238 to 235. So then the atomic number or charge atomic number is 92. Now let's look all types of the decay we have. We have here an element we don't know, okay, and we are producing out of this element here. We are producing out of this element first alpha decay. So this is called alpha decay. We have to know what the element is that. So next, you can produce something here. We have beta decay, 0 minus 1. This is beta decay. And we have to get this element, what this new element is produced. So we have to know what this element is produced. So number 3, we have positron. We have alpha, beta, gamma, and we have neutrons. We have neutrons, and then we have protons. And the last thing here we have gamma. Okay, guys. Now, this we'll learn before we have to determine the elements. We know something called nuclear equation, and the topic is balancing. Nuclear equation. So balancing nuclear equation. So we want to balance this. Well, in order to balance this nuclear equation, we go first, the atomic mass or mass number at the left has equal to, remember this question mark here, we'll say this here, we don't know. So let's here have this one here. This is X, correct? This is X. So the atomic mass at the left is equal to the atomic mass at the right. Here I have 4. So I need something to keep up this to 238. So how much will be here? 2, 3, 4. Why is 234? Because if I have this 4 plus 4 will make what? 238, correct? So the atomic mass of this unknown element coming out, a new one, is 234. How about the atomic number of it? I have here 92, but here at the left 2. So how much here will be? 90, correct? So I go and look at the atomic number. So this will determine the element, determines the element. So it is new element, yes. What's the 90 is? Thorium, Th. So therefore, this element here now, this element we'll take the whole thing here out, write the correct answer. I'm just writing the next. Here, guys. So this one here, I will put this one red. This is Th234 atomic mass or mass number, and 90 is the atomic number. So atomic mass number is 234, and it goes by atomic number. I can know what the element that really is. How about next step? Come on, you can tell me now. Can we write what's this? What is the top will be? 2 what? 238. Professional. Very good. Perfect. 238. How about the bottom atomic number? 93. Perfect. So 93. What will be? Neptunium. NP. And this is 93. Because if you add this with this, has equal what? 92. Correct? That's easy. So let's take number 3. Now you should tell me what that will be. So what's the mass will be? 238, the same thing, correct? That's 0 here. So the top 238. How about the bottom here? 91. 91, a new element? Yes. That's 91 is, protactin, SPA. So always goes by the atomic number. So how about the next one? Now we are very professional today. And I'm really stunned. Today is Monday. Okay. Very impressive. For Monday, I mean. Okay, so what will be with the neutron? What will be the top now? We have to watch. How much is the top? Okay, 237. Perfect. 237 because we have one in the tier, neutron, correct? How about the bottom? 92. The element will remain what? Uranium. 92 is uranium. Just another isotope of uranium with atomic mass different from 238, 237. Perfect. How about the next one? How much? This is 1, will be what? 237, that's correct. So this is 237 because hydrogen is 1, correct? How about the bottom will be? How much? 91, correct? PA. Okay, guys. How about the last one? The last one is very funny because you get the same one is out. no mass, no charge, no atomic number, no atomic mass, correct? So you can expect the same one coming out, 92 and 238. You get the idea, guys? This way we call all those are decays, and this is part of the nuclear reaction types. And at the same time, we are balancing nuclear equation. We are balancing what? Nuclear equation. Any question about this? Any question about this? Okay, so the last topic is, that's the whole thing. We finished the chapter. Almost. Okay, so cool yourself down. Cool yourself down. So can I take this one out? Everybody has it? Okay, let's take this one out here. Okay, let's take this one out. So let's well, I'm not running quick. I just want to make sure we understand. Let's take challenging worksheets here. That's very good. Time is very good. So let's take a challenge here, and then let's look at the one of the worksheets. And then we'll go for the last topic. The last topic here it is. So now, if you look at this chapter 3 worksheets, you can download them here. Download, because they're a zip file. We can't open them as they are. We have to download them here. And show in folder. And then we'll take them, cut them out. And then we can paste them here. Okay, so okay, so let's look at the, you can tell me, balancing nuclear equation and half-life. So we did all cover all this, and then we'll go for half-life and two type of reaction we know. So let's take 7. I don't know what they are. Okay, guys, there is no answer here, but they give you the answer. We have to circle one, multiple choices. Identify. Let's do maybe 1, 2, 3, 4, 5. Look at them first, and then you decide which one you like. 1. Let's look at 1. Let's look at 2. Let's look at 3. Let's look at 4, 5, 6, 7, 8, 9, 10. We'll not do all of them. We'll do look at them, see which one you think. Wow, that's a lot of them here. That's a lot of them. So that's 7. That's good. It's multiple choices, and you tell me what's the answer. So which one you like now? Let me go up front here. Which one you like? Which one? We'll take 3 or 4. 3 or 4. And then we I don't want to finish. I'll finish chapter 3 by next Wednesday. So that's quick. Which one? 4. Okay, yeah, number 4. So let's do number 4, guys. And there is an answer there, though, correct? Multiple choice. And we have to get the correct one. So, guys, how many atomic masses, because we have 2 elements. We have to add those atomic masses. So let's write it here. So we have here how much? 27. And here how much? The sum is 31, correct? How about here we have what? 30. So whatever the particle will be, remember the particle missing will be always those 6 decays. Alpha, beta, gamma, correct? Positron, and then neutron and proton. So we have 1 in the top. I'll say 1 in the top. So And how much in the bottom we have? 13 and 2, how much? 15, correct? I'm adding up. I have 15 here. 0 at the bottom, correct? That's 15. 15 and 31. That's the sum. So what will be this one here? 1 and 0. It has a mass of 1, 0 charge. Come on, don't let me know. Don't let me down. Oh, sorry. So what is this? Correct. Don't be shy. Just say it too loud. Say it too loud. Don't be shy. So this is a neutron, correct? The neutron always has a mass of 1, a 0 charge, 0 atomic number, correct? So where is our answer will be? Where is our answer? C. Make sense? Good, good. We have 10 minutes. I'll spend 10 minutes on those sheets, and then next time we'll come and look at half-life and look at half-life and 2 types of reaction, fission versus fusion, and that's it. That's the whole chapter. Very, very small chapter. It's not that very, very large chapter. So, which one you like? This is 1. We did 1, correct? So, which one you like? Let me just. Which one? 6, 7, 6. Okay. What came out of 6? That's what I want to know. What's come out of 6? What is this? What we call this? What's the beta, correct? That is what? Beta, yeah. Not electrons. Electrons are valence electrons, they're outside. But this is beta, or electrons coming from the nuclei themselves by collision. So what will be in the top here, the element in the top? How much we have? 99. Perfect. How about the bottom? 44, correct? Everybody agrees? What will be our element? 44. Look at that. Where is 44? Atomic number. Atomic number will give us the element. 44 is what? Okay. Ruthenium, Ru. So where is it then? What's the choice? What's the choice? A. It is not Monday today. I'm very impressed. So it's A. Okay. So let's take another one. I'm not going any for the next one. Next one is easy. The half-life and the vision. I'll finish the chapter. That's not fair. Let's extend it to the Wednesday. So let's take another one, because that's all the chapter is all about, balancing nuclear equation and then calculation of the half-life calculation. That's all. Even the units, we don't ask our students about the units. But I can show you the units are there, but we can talk about them Wednesday. So which one you like? 5? Oh, 5 is a good one. 5 is a good one because it's a lot of calculation. That's a good one. That's really a good one. But it's already everything given to you. It's a factor here. That's a factor here. Multiplied by 3, multiplied by 2, multiply 3 neutrons or 5 neutrons. That's what it says, correct? So let's see. It's a factor. So the factor here is tell you 1 or 4. Here they are here. Multiple choice. Are there 4 neutrons coming out? 1 neutron, 3 neutrons, or 2 neutrons? So that's what so what do you think? So 2, 3, 5 plus 1, how much we have? 2, 3, 6. Correct? In the left side. And at the bottom, how much? 92. So now calculate for me. 95, keep this one here aside. Keep it aside. 95 and 139. How much is it? 4, 3, 2. So how much is missing? 2, because here 236. Missing how much? Who said 4? But 4 is too much. Yeah. How much is this? 2. But I have here 1, correct? So what's the factor will be here? 2. So the answer is A. The answer is 2A. Make sense, guys? Okay, another example. Let's take another one. So which one you like? Well, where is the hardest one? Well, I don't know which one. It is which one? Which one? 10. How about 10? Let's do it 10. 10. I like it 10. We did similar to that just a couple minutes ago, correct? 10 is good. So what will be the answer? Somebody will tell me? So how much will be? 236, and the other side is 92. 92 is okay, but how much? Don't let me down, guys. Let's do it together. So here, how many you have? 236, correct? One is here, and 235, 236. How about the bottom? 92. So keep this one aside. Don't touch this. 94 plus 139. 94 plus 139. This is 3, 3, 1. Correct? So how many missing? 3, correct? How many missing? 233 and 236. How many missing? 3, correct? So what's the factor will be? The factor will be 3. The factor will be 3. So the answer is C. Correct, guys? So let's take another one. We have a couple minutes. We'll finish as much as we can from this, and then Wednesday we'll cover the half-life and the fusion and fission reaction. The units will not go through it, but I can show you the units. Okay. So let's take this one out. Let's select another one. How about 11? 11. Let's look 11. Tell me 11. So I have 226 and 88. So what will be the bottom or will be the top? The atomic mass at the top, what will be? 2, 2, 2, 2, correct? The top. 2, 2, 2, atomic mass, correct, guys? So how about the atomic number? 80 what? 86, guys, 86. Now we are turning to our actual Monday. 86. What is 86? Look it up. Radon, correct? So the element will be Rn, radon. Okay, guys? Radon. So where is it? Radon is radon 22, 86. Okay, guys? So we have still 2 minutes. Cool yourself down. Cool yourself down. Cool yourself down, guys. So how about 16, guys? 16. That's a good one. That's a good one. That comes in the quiz. It comes in the final exam. 16 is typical because a lot of students are confused. So how much in the left? Atomic masses? 2, 4, 5, correct? How much is the atomic number? 90 what? 7. Now, we have to be careful here. I have how many here? Atomic mass? 2 already, correct? So what will be in the top will be? I have 2 already here. So it will be 2, 4, 3, correct? 3. Why is 3? Because I have here, the neutron is 1, already 2 here. 2 multiplied by 1 is 2. 2 multiplied by 1 is 2. So 2 plus 2, 43 will be 245. How about the bottom atomic number? No, it said the same, but that's the sum is what? 97. What is 97 here? Look at it up. Berkeley Lab, Berkelium. Most of the lanthanide, actinides, those are cities or labs or scientists. So BK. Okay, guys. Okay, that's it. Thank you very much. We'll come and finish chapter 3. Uh, thank you.